Experiment 2. Recrystallization of cold-worked metal. Please refer to the study guide for general comments, rules and regulations, as well as criteria required to successfully complete this experiment. The term cold work refers to any plastic deformation that a material experiences at a temperature that is below that particular material's recrystallization temperature. Cold work changes the shape of the material as well as some of its mechanical properties. When a material is cold worked, the grains become thinner and elongated. This graph shows the effect that cold work has on a material. It can be seen that as the percentage cold work increases, the material experiences a reduction in ductility and an increase in both strength and hardness. Once cold work has been completed, it is possible to heat treat the material in order to recrystallize it. This is achieved by placing the cold-worked material into an oven or furnace at a temperature above the recrystallization temperature and below the melting temperature. The second graph shows the different stages of recrystallization and the effect that it has on the mechanical properties of the material. Take note that the x-axis of the second graph is temperature. This means that the material is placed in an oven or furnace for a set amount of time at a range of temperatures. The same effect can be achieved by keeping the temperature constant and increasing the time that the sample is left at temperature. The first stage of recrystallization is called recovery. During this stage, positive and negative dislocations move towards each other and eliminate one another, resulting in a small increase in ductility. The second stage of recrystallization is also called recrystallization, and during this step, the elongated grains are replaced by smaller, equiaxed grains. The driving force for this stage is a reduction in internal energy. The third and final stage of recrystallization is called grain growth. This occurs if a material is left at temperature for extended periods of time. During this stage, grains will grow at the expense of neighboring grains. The driving force for this stage is the reduction in internal energy by minimizing the amount of grain boundaries that are present in the microstructure. Here we can see micrographs of cold-worked material, recrystallized material, and material that has experienced grain growth. The objective of this experiment is to determine the effect of cold work and recrystallization on the microstructure and mechanical properties of brass or aluminium. Please pay close attention to the practical demonstration. Measure the thickness of all the samples using a vernier. Assume that the thickest sample has experienced no cold work. Using the sandpaper provided, grind off the oxide layer that has formed on the material. This is important because the oxide layer could affect the hardness measurements. Ensure that you measure the material thickness before sanding off the oxide layer. Perform hardness tests on all samples as demonstrated. Place the sample on the anvil underneath the indenter. Turn the hand wheel until the indenter is touching the sample. Turn the wheel crank in one smooth motion until the small hand on the dial is in the center of the red dot. Adjust the dial so that the red 0 is in line with the large hand. Pull the crank handle forward. Once the second crank handle has moved completely forward, push it back to its original position. Read the value off the inside scale. In this case, it can be seen that the reading is approximately 61 Rockwell hardness on the Rockwell B scale. Record these values and complete the practical sheet provided. Place 5 samples of the highest percentage cold work into the oven. Make sure that the samples are in the center of the oven. Remove and quench one sample after it has been in the oven for 2 minutes. Repeat this process at 5, 8, 14, and 20 minutes. In order to maximize the time efficiency of this practical, it is recommended that this sequence of events be followed.